everyone. Let's start our event tonight. This event is hosted by Open Innovation Lab. We call it OIL. And Open Innovation Lab is now officially supported by the IE department in CUHK. And usually we will have the meetup every Friday night like this. We invite some talented people to share their project or their religious experience with us. And you are very welcome to be a member of our OIL community. If you want to share something, you can contact me and I will arrange the events accordingly. And tonight we are very pleased to have Wei to share his project, Microkernel development. Without further ado, let's welcome to him.
I'm going to talk about, like this is a project I've worked for nearly a year, just occasionally, but I guess this is the longest project I've worked on. It's a microkernel project and called Rex. So first go through some overview, just make sure you know what I'm talking about, and then do a short demo, and then we go a little bit about what actually happened in the demo, and then we talk about actually two things: memory management and system calls. These are the things that I found challenging to work with. So also a little bit about interpersonal communication, and this next step is about something I haven't got time to implement. And yeah, so let's get started. So microkernels, this contains a few slides from the last talk. So if you are here in January, just don't fall asleep. Microkernels first is a kernel which we try to isolate time and resources, space and resources from different processes, and also manage communication between them. So it also needs to allow those processes to talk with the outside world, other hardwares through I/O or other means. That's basically it. That's what you need about microkernel. So there are a lot of microkernels. I guess the oldest one is called Match, and there are also mini export. And also in mobile phone, you always have two kernels. So the first one is probably under iOS. The other one manages the communication with all the mobile communication, and that is actually a microkernel. And we also have the alpha family microkernel. So compare with microkernel and monolithic kernel, we want to make more things to run in user space. So for here, the monolithic kernel, we run the file system, the scheduler, virtual memory, device drivers, all in kernel mode. But in microkernel, we want to only have some basic IPC and scheduling memory management, and we want to make those device drivers, those file systems, into user space. So the advantage of this is that if you have some bugs in this part, then your kernel will just die. But if you have some bugs in this part, then your kernel will continue to run. You probably just need to restart those processes. And also there are some safety reasons, and also this is a hot topic in research. Research don't have a lot on that part, so I talked about the alpha family tree, which contains very long, and I only want to talk about the IC alpha here, which is relatively new. It has a formal proof. So the proof is converted from Haskell to called Elizabeth proof checker, which checks the microkernel actually does what it says it does. Yeah, it has a Haskell model, and it has around 8,000 lines of C and 600 lines of assembly. And this kernel is reasonably fast. It's actually really fast. So yeah, so the kernel I'm working on is called Rex, and it tries to adopt a design similar to ICL4. And I also try to use Rust, and also ensure Rust constraints about memory safety. Yep. So the current status, so those are parts that are basically finished. Some parts like the IPC and scheduling are finished this afternoon. Deadline is the best motivation. So yeah, but I mean those parts all have the semantic in the kernel and it actually works. So I think now I can finally entitle Rust as a real microkernel rather than like a ongoing project. So here are some status. So I have around 6,000 lines of code, and most of them are written in Rust. There are only a few of them, 100 of them are in assembly, which is great. There are actually some inline assembly in the Rust code, which probably contributes to like 200 something. But that's basically it. So it is not entirely finished. So you will say we still got a lower amount of code than ICL4. But after it's finished, I will try to reduce the amount to be less. So I will then first talk just a little bit about capability, which is the alpha, which is a way to manage do memory management and scheduling, and then to show the demo because the demo is based on the capabilities. So capabilities is basically smart pointers. Those smart pointers pointing to resources managed by kernels. And they have some properties. For example, those capabilities can be addressed in user space. This is using something called say address. And some processes would own some capabilities. And in that way, we solve the permission management problem. So we don't have, like, in some L4 family kernel, we have 3 like privileged users, and in Linux we have the root. But in ICL4 or Evax, we don't need any of them. We just manage capability. And this avoids the confused stupidity problem. For example, just give the file system an example. So for example, some code may just want to access a single file in your document folder, but you often, like in Linux, you need to give the process access to your whole file system. And in that case, if the process misbehaves, it may try to read other files, write other files, and that is what is called confused stupidity. And if we try to manage use capability really well, we can avoid this problem. We have capabilities, and they are pointers to kernel resources. So we also solve the problem for system calls. We just make those system calls invoking capabilities. And those capabilities are actually ICL4 in Rux. They do all the job of memory management, scheduling, and other primitives and inter-process communication. So those are the capabilities that currently in Rux. There are something called untyped hub, which is just an initialized memory. So those are memories that are free and can be used for other purposes. So we hold some untyped capability, and then you can retype those capabilities, like create new instance from them into those capabilities. So we have the capability pool capability, which is just a capability that contains multiple capabilities. And we also have paging related capabilities. So this PML4, PDPT, PT are all the architecture specific. So they are all specific to the Intel's paging management. And also we have the page capability. So there are actually two kinds of them. The first is raw page capability, which you can just write anything in it. And also we have text buffer, which is used to manage some text-related things. For example, to manage the system call, return value, things like that. We also have used VGA buffer to in it. The paging capability manages the VGA buffer. So for CPU time sharing, we have the text hub, which each text hub creates a new process, and they contain a reference to our capability pool, so it can have a state address to addressing different capabilities, and also it will contain something related to paging capability, so it can switch to different pages. And we also have the inter-IBC capability, which is called channel cap. I will talk about this later. This is same as the endpoint capability in ICL4. So this is just an example. So how do we use those capabilities? So this is how you create a new task or a new process in ICL4 in Rux. So first you create an empty text cap, and then create an empty CPU cap, so you can hold some different, you have a capability pool to hold different capabilities. And then you initialize all the paging capabilities, so you need one PML4. And on top of that, you initialize different PDPT, PD, and raw page capability. And then you can assign the stack pointer in the text cap to something, to some pages you have already allocated. And also you need to load the actual program into those pages. And after that, you just need to assign this PML for this paging capability to the text cap, so it knows how to switch to different pages. And also assign this page cap, simple cap to this text cap, so it knows how to address different capabilities. And now you can just switch to the text, and that's basically how it works. So just a quick demo. This works. Okay, so yeah. So right now I'm in this folder, and I can try to run the kernel. And it will fire up something. So this is the VGA buffer, and this is the serial, which also points a lot of logins. So in this VGA buffer, I can run some simple command like echo So just to show you an example, so this is actually debugging capability. So if I do a last, it will show all the capabilities that this process. This is running in user mode, so it's running by a task app. And when I do this last, it will show all the capabilities that are currently owned by this task app. So if you look into the kernel log, you'll see there are some untagged capability in the top, a simple capability on the top. So that is the simple capability that is addressable, and we also have those PML form and the page capability, and these three are architecture specific, so they are PDPT, PD, and PT. And we get also a lot of the page capability because this program is actually a little bit big. Yeah, here are two other architecture specific ones. And on the bottom, a little bit more page capability. This is also architecture specific. So I guess the last one, this one is where its stack pointer is pointing to. And we also have this channel. This channel manages the keyboard. So the program will always try to wait on this channel for a new keystroke. And so here I can also do retype. So I'm trying to retype an untyped cap into a simple capability. So if you look at the top, we once got something with index 2 that is an untyped capability, and I can put any index. This is just a free index that I want to put the resulting simple capability. So if I do that, and I do a last again, and you will see here, this one is newly created simple. So in this way, this user program is now finished. So just by using this way, create a new simple, create new task capability, create new paging capability, you can develop like a full operating system in user space from yeah, so that's for the demo. So just under the hood, wait a second. There is so under the hood, what has just happened? So behind the scenes, I run the make run. It tries to involve a new QEMU, a virtual machine, and try to use the multi-boot thing, so I don't write a boot loader. I just skip that part, just jump into the kernel as quickly as I can. So yeah, so there are some startup assembly to check for CPU ID, which check for various CPU capabilities, like whether it supports 64 bits and whether it supports advanced program interrupt controller. And then I set up some initial padding and also GDP and other Intel structure, data structure stuff, and take a lot more, and then just switch to Rust. So in Rust, the multi-boot has some information given to me, so I can get the free regions of the memory from the multi-boot data structure, and then those actually contains lots of code to initialize the paging, initialize the segmentation, and initialize the interrupt. That's probably the thing that takes longest to write. And then finally, I can switch to Cayman, which is the actual kernel stuff. So in this K-man, I just do what you have just seen about creating a new process. So just, if you want to recap, just create a new task capability, create a SQL capability, and initialize all the paging, and assign the stack pointer and load the program. So the program is also in this init.rd. This is the program I'm going to load. And then get the program assignment and then just switch to this task. So when I finish creating the task tab, so this takes me a while to get this several lines of code to work correctly. So what I'm doing here is I run a text switch to, and this switch to might be returned by some interrupt. For example, a timer interrupt or keyboard interrupt or something like that. And I want to make this function actually return, and it gets back to me an exception. So then I just do a handle exception and then continue to do this while loop. So that's currently how this scheduling is handled. So just logging around scheduling, but it actually works. So then we come to the user mode, which we have already had the VG buffer that is managed in the K-man to map into a known location. So I then just write something to that VG buffer memory location, and then you see what things pointed to the screen. And also need to do some kernel calls, for example, waiting for a keyboard input. That is just waiting for things on the channel. And when it returns, you get a new keyboard input. So next, so that's actually what happened all in the demo. So next are two things that I found challenging to implement for this kernel. The first is about the smart pointers, how those smart pointers, the capability actually works. And the second is about kernel calls. So first about those smart pointers. So I mean, if we want to have, because those capability are smart pointers to those resources, and we want to have something that is reference counted. However, in that case, because we have SQL, and those SQL can hold some capabilities, and also it probably can contain itself, because sometimes I want a task to manage its own SQL capability, and in that case you get circular reference. So in order to break that reference, we need something called strong pointers and weak pointers. That is standard data structure. But what doesn't work in the kernel is that our resources, for the standard data structure, our resources only get freed when all the strong pointers and weak pointers are freed. That is unacceptable in this kernel, because what I want is when those strong pointers are freed, I can allocate those freed memory to some new resources. And so I need to, when the strong pointers goes down to 0, I need to free all the weak pointers. So that is something that takes me a while to implement. So the solution is what I call the weak pool. So what I got is basically a double linked list, and when this when the strong pointers are all freed, I have a reference from the resources descriptor into every single weak pointers, and I just deallocate all the weak pointers. Just recursively deallocate all the weak pointers. And because Rust doesn't have move semantic, which creates some problem, but it actually worked. So using this solution, we can actually just represent the capability pool just as a weak pool, because that's what it is. And also for this PML for KPT, because we need to know that whether those paging capabilities are actually met. So it also needs a pointer, and this pointer is a one item weak pool. And for test, we need a pointer to PML4. We also need a pointer to a C pool. And we also need a pointer to a text buffer, so that makes it a 3-item weak pool. So this is a side note about memory management. So because this is a microkernel, so I want to delegate as much work as possible to user space. So in the kernel space, the untyped implementation is very simple. So it just have a watermark, and each time it tries to increase the watermark to allocate more resources. So if we actually want to free memory, we just reset this untyped. So delete all the resources that derived from this untyped. Yeah, Rust have a lot of guarantees for memory safety. So if we write in safe Rust code, it's guaranteed that you don't have downlink pointers. You don't have a pointer that is point to non-resources, and we also don't have a case when we read uninitialized memory. And we also don't have data writes. So those things are enforced at compile time. However, it considers safe to have those things deadlocked, which happens a lot in the kernel development, actually for me. Yeah, so these are the things I'm not guaranteed. But even just with those three, it actually works a lot. So we have the kernel mapped to the higher address is always FFFFF and 80 after that. So and the kernel will only address those addresses. So it's use something called an object pool to access things in the user space. Yeah, and they have also PML4 with kernel address space mapped. So in this case, the kernel address space is always available. So I would make sure that when I access a kernel address, it won't trigger page faults. And text switching will return by interrupt. As I've said, it's just like a function return. And in this case, surprisingly, I can make text switching and also the page switching safe. So in that case, it won't have any memory safety issue. For memory management, I also have implement logs. This is for multiprocessor. Just for the future, it haven't been there, but just use log to make sure it will support that. So most kernel objects are read-write log, so you can have several different threads or processes reading the address, but can only have one process writing to that object. Of course, there are some arguments. For example, the ICL4 team, they try to argue that a single global log might just be enough for some kernel considerations, but that's for another talk. Yeah, and the second thing as I talked about is about the system calls. So if you actually look into the code, there are a lot of assembly in that, just to make sure that when I call a function that switches to user space, it actually returns. This actually takes me a long time to implement. And for this part, debugging is basically impossible. Just you don't, because most time you just don't know what actually went wrong. Even just you look at all the CPU registers, but you don't know what the CPU actually looked at. So so the only thing I found useful is just to read carefully through the Intel's manual. Just make sure you don't miss anything, make sure everything is there. And then, yeah, I actually spent like 2 or 3 weeks to make this work, but it finally worked. And it relies heavily on in Rust or in C, you have something connected function, which is really suitable for writing interrupts, and also a lot of assemblies. And for inter-process communication, in ICL4, they got something called endpoints. So if you just look carefully about the endpoints, it's actually in a lot of programming languages like Go, Clojure, like Racket. It's actually a channel. So I just call it the URL name, a channel. So a channel is very simple. So it has 2 functions, put and take. So you can put something onto the channel. If the channel has already had another put waiting, then this put will block. And the take is the same, so the take takes a value from the channel. If there is no value, the take also blocks. And in that case, this is how the keyword is implemented. So there are something for, yeah, that's basically what's currently in the kernel. So then there is something about the next step. So first about scheduling. Currently there is only a simple roaming around scheduler, but actually this is something I want to implement. So we want to make a CPU time abstraction. Basically we want to associate have a scheduler that holds 100% CPU time, and then we use the same retype, or in this case we call it mint, to drive new capabilities with smaller CPU time from this overall capability. And the kernel do a round robin, so we probably get one tag that holds 4% of the CPU time, or another probably 2%. So using this case, we handle priority. Yeah, and for different CPUs, we have different overall CPU capability, and we don't actually handle those SMP stuff in the kernel. That makes the kernel simpler. Yeah, so we initialize multiple CPU time capability for multiple CPUs. This is something not implemented, but I guess it's simpler than ICL4. ICL4 just have a simple roaming round scheduler with priorities, and those priority stuff really make it a little bit complicated. So what I want is to make those priorities and the other unnecessary stuff to be implemented in user space. Also, this is something I haven't been implemented in notifications. it seems similar to channels, but just when I send something to this notification object, it doesn't block, so it just will bitwise form. And also for exceptions, some tasks may have certain exceptions sending out, and in that case, the correct implementation is to have an exception endpoint that other capabilities can be meeting. So in that case, like all the exceptions will go through this endpoint, and this is not yet implemented. So yeah, so that's basically what's been there. Right now I'm focusing on some enhancement, like performance. The performance is not really good. So this enhancement of the current functionality. So if you want to hack the kernel, you buy some documentation and scenario in January. It's not there at all right now. And please try to stay out the code and build your own kernel. So currently, I try to make all the scheduling stuff and all the memory management stuff really simple, and it's really like if you code compile, it's really hard to make it to get any memory corruption or things like that. So this code base is probably good if you just want to explore some higher level OS stuff like advanced scheduling or advanced memory management. Yeah, so that's basically it. And currently you can find the source code here. If you want to hack the code before January, and you want some documentation or you want some clarification, just send me an email. I guess that's it. So any questions?
Thank you.
Yeah.
Yeah. Previously you said for microkernel there are some you can use some machine tracking proof to prove the system was as you want. Did you prove your one microkernel?
No. I mean this one. So this SCR4 is the only general kernel that got a formal proof. It's not that simple. So how they did that is they tried like many years first to get a correct kernel model.
Mm-hmm.
And using that kernel model, they create some Haskell code. So it's basically a virtual machine. And from that Haskell code, they generate those some proof code and using.
So automatically.
Yeah. So I guess not entirely automatically, but from Haskell you can generate some immutable code, and that's probably how they start to do the proof. Oh, I see. Yeah. So it's just a proof that their kernel does what it does. Mm-hmm. It's not a proof that it's perfectly secure or anything like that.
I think so, yeah. It will be difficult.
Any other questions?
Could you show us the system call you like we are using the Echo, and so what is the API looks like?
So you're probably
Say where is that? Here.
So this Echo is just execute command. Yeah, this echo is just for like error checking, make sure I get this correct. So it will, if you are using this echo, it will use this point macro, which in this case will go to this VGA buffer file. And here, it will try to write a single byte at a time. So this is just writing all those things into a null location. So if you say, here is a code, yeah, here. So this is just a null location. It will, the kernel will always map the VGA buffer to this memory address, and then you can just write bytes to this memory address to write something to the VGA buffer. So it's if I remember correctly, it's 25 times 80. But most, I guess you would most be more interested in the kernel calls, which are here. So you get a function. This is an API called channel take, and you try to access a capability with index of 254. And then this channel will return a new scan code, which we can just turn this scan code into a key, and then do all the printing stuff. So how this system actually works, it is here. So we get this system calls, and it will write something to the buffer and just do this interrupt in assembly. And then this code will go back to the switch function, which you see there are a lot of assembly code. But what way will be going is here. So this is return. And first I need to save all the user mode registers. And then when I return, I need to just apply them again. And then here I try to, for the interrupt, I got the acceptance stack, which I need to store this acceptance stack somewhere else and restore my own registers in the kernel. And then this one will return to, if I remember correctly, here. No. Here. This switch to function, which I just do some other modification about the exception I get. I return exception type. And this will then go back to 11, this one. So here you'll see there it will actually handle the system call from here. So if I do a channel take, then I need to wait for the channel to have some value, then the text need to wait. And if there is nothing or the kernel is idle, I just run an idle process to wait for new interrupt, or wait for the timer is not enabled yet, just because it's not very useful right now. And just there is a value to call those tasks again and again to do all the scaling. Yeah.
Oh, okay. Some follow-up questions. So the printf you have written is just basically write to the VGA buffer.
Yeah.
Okay. And the way you handle system calls is actually like interrupt. You have a kind of index. It's like vectors and interrupt. So
Are you in the interrupt table?
Yeah. The way you handle system calls is kind of like interrupt table, right?
Yeah.
So what is the like state of art way of doing this like system calling like Linux also? So this seems a little like ancient.
You mean the?
Yeah. What's the modern way of doing these things? All people are you using this way currently?
Can you just repeat the question?
So what is the way people writing like modern kernels, not like probe content kernels, handle system calls? Like you are using kind of an index, right?
You mean no? No, it's not. So for the index, it has something called interrupt maker, and for system call, this will always be 8.0. So it will.
You have a preset like system call number, right? So you call a certain kind of system call using that number that you are printing.
Oh no, that is for the. So that is here. That number is used here. So. That number is to determine which channel I'm operating on. So. Yeah. So for that interrupt table, we get there are multiple Intel data structures like IDT, and also there is one in segmentation called IS. If I remember, TSS. Those are the two tables you need to set up for to get the correct function for interrupt calls, and also for those keyboard or for timer, you can set up something like PIC for IR2, or for modern Intel system we have APIC and IO APIC that deal with those stuff. So that's the low level interrupt handling stuff. Yeah, but for this case, this is not like I mean, I probably should refactor this code. This just do like I have this system call which is a data structure, and it will just try to based on which the actual type of the system call to do multiple stuff. Yeah, but I probably should like refactor this code to get it into different functions. Yeah.
Last question. So there's no type in Rust, so you use that in this.
There is a lot. There is full of types in Rust. You can say there is no type in C, but there is full of types in Rust. So for this one, why we don't need to explicitly determine the type is because it can be like that referred. Yeah, because this clone already got the return type for it.
Okay, if we have no further questions, we can go to the next room and we have some short trip. We can have a free discussion with the speaker. Thank you.